technical stuff, so it wasn't. It was like basic concepts, review of the basic concepts, and repetitions of the same concepts in terms of rotational motion. Today, we're finally at some point we're going to start doing real physics, the fun stuff. All right, so I'm going to emphasis on something that Galileo came up with, which is this free fall. And his
Galileo had spent half a lifetime trying to prove the Earth moves. Now, he would come to terms with something much more basic, the mathematics of motion itself. But motion is hard to measure.
It all happens just a bit too fast for you to see what is going on. Galileo hit on this wonderful idea of slowing down the motion. So instead of trying to watch a thing falling, he rolled balls down very gentle slopes so that the speed built up very, very slowly.
Galileo reasoned that as balls rolled down slopes, they would accelerate, just as they did in freefall, but more slowly. As a young man, Galileo had designed a very accurate inclined plane, one of the most important pieces of experimental apparatus in the history of science. Galileo left behind no plans for his inclined plane, but based on his experimental notes, Professor Roberto Caparelli is using what he believes to be Galileo's original design to discover how he was able to accurately measure acceleration.
Galileo studied the inclined plane, slowing the motion of falling bodies until he was able to observe the phenomena. He was able to measure exactly how fast a ball would roll, timed to the swing of a pendulum. Galileo was sure that the steady acceleration must be governed by a mathematical rule.
So he takes this very gentle inclined plane and he lets the ball roll down and he watches how that ball speeds up and he measures how far it goes in a certain time. And then he makes his first empirical discovery that if in the first unit of time it goes 1 unit of distance, in the next unit of time it travels 3 units of distance, and in the next 5 and the next 7. So it has this beautiful numerical progression, 1, 3, 5, 7. And he calls this the odd numbers rule. And he really is entranced by this. He knows he's made a huge discovery.
Galileo had found a mathematical rule for accurately predicting the motion of objects in the real world, a universal law which applied to any falling bodies.
Underneath this beautiful empirical law that he found a deeper law, clearly a deeper law, using mathematical logic and deductions. And this was actually the key to all the later great successes, first of Newton and then of Einstein and all the other wonders of modern science.
As a young man, Galileo had revolutionized astronomy. But at the age of 74, his last great book revolutionized the physics of motion.
From the point of view of physics, his most important contribution is his discourse on the two new sciences. Indeed, it's that book that provides the real foundation for Isaac Newton.
Right, so the basic premise of the Galileo's inclined experiment is to figure out what gravitational acceleration is. That's it. I mean, today we got the technology, but that lived like 400 years ago. So the problem was really, really fast, right? I mean, you can't tell whether it's falling at a constant speed or if it's accelerating. Yet this guy knows it's accelerating because it goes from 0 to something else, right? So what do you do for him to be able to figure out what that acceleration is? It puts the ball on an incline. So the ball starts rolling. It looks at the distance during the first second, compares the distance during the second, the third second. During the first second, it goes 1 unit of distance. The second, 3. The third second is going to be 5, and so forth. Okay, so he notices the patterns, and then he makes the calculations and figures out the gravitational acceleration. Except the problem with that approach is you're using an incline. In this case, the ball is going to roll, right? So when things are rolling, does this mean that everything is still going to speed up at the same rate? It's important. When you have a solid cylinder versus a hollow cylinder, do you think they're going to be speeding up at the same rate? Do you think they're going to accelerate at the same rate? Do you think they're going to reach the bottom at the same rate? All right, I know they're going to fall at the same rate, but you think they will accelerate at the same rate while they're actually rolling or rotating? And all of a sudden, it turns into a weird problem. It's a bit of a mind twister. Falling chimneys, notice that it nearly always, they will break at some point. So what caused the chimneys to break? All right, different portions of the chimney is going to be falling at different rates. So why is that ends up breaking right after that point? Velocity and falling without braking. End up braking. That was weird. It's like a million of them. Okay, after you guys have seen like almost 15 towers dropping, what's your theory on that? Does somebody have a theory? As it's falling, it starts to break apart. I think it's gonna. Okay, notice that it broke apart right behind it. What causing that to happen? Does anybody have a theory? People are clapping and they're so happy. All right, this is the last one. Just want to do one more, just for the hell of it. Okay, let me ask you this: what are these chimneys for? Does anybody know? They seem to be all over the place. Okay, rotational. Mark, I need more than that. I'll give you 5 points. Yeah, it's rotational acceleration, but I need more than that. I mean, these chimneys. They build these chimneys because they want chimneys. Notice they just. Oh man, it broke up at 4 different places. Okay, unpaid for coal plants. I have no idea. I did this. You have no idea. Anyway, so you guys have seen enough. So that's one of the things that we will investigate. The pilot in a centrifuge acceleration. I'm not interested in that. Okay, let's move forward. Enough time spent watching chimneys. That was fun. It's a nice COVID activity. All right, angle displacement, fast review. Means angle. Upper unit is going to be radians. Pi radians is 360 degrees, and 1 revolution is 2 pi radian. That's it. All right, so the best answer put in the chat. Put the best answer in the chat. All right, so B is the best answer. Angular velocity. How fast the angular displacement changes in time. Go from initial angle to final angle. Proper unit is radians per second. And the best answer is B. All right, so you guys. Angular acceleration is how fast the angular velocity changes in time. How fast you go from initial velocity to final velocity. Proper units can be radians per second. Squared. And the best answer is, it's hard work. It's hard work. So the best answer is going to be it's radians per second squared. You guys got it. Moving forward. How do you do transition from angular to tangential variables? All right, so if you know the rotational displacement, you can figure out if you know the angular displacement or rotational displacement, you can figure out the curvature, length of the curvature at a radial distance of y. So the length of this curvature is known as the arc length. So if you know the rotational displacement multiplied by the radial distance at that point, it's going to give you the arc length at that point. If you know the rotational velocity, you can figure out the tangential velocity, linear velocity in the direction of the curvature. So that's your tangential velocity. If you know the angular acceleration, you can figure out the tangential acceleration along the direction of the curvature. As your angular terms are on the right, if you multiply the angular terms by the radial terms, radial distance, it's going to give you tangential terms, linear terms on the left. All right, so who has a greater angular displacement? It's going to be the same for both, right? So C is the best answer. Okay, so the fastest linear speed is the same as tangential speed. So the best answer is going to be near the outside. Angular speed is the same, so it depends on the radial distance. So outside is going to have a larger radial distance. So B is the best answer. All right, so who has a greater angular speed? Angular speed is going to be the same for both of them, right? So C is the best answer. All right, so what do we have? What do we have? All right, so it's a rigid body that's rotating. The correct statement is all points on the body are moving with the same angular velocity, so B is the best answer. It's got centripetal acceleration as well as rotational acceleration. So when you have two different accelerations, how do you know what the total acceleration of the system is? All right, so it's going to have two accelerations. One is centripetal acceleration. The other one is going to be rotational acceleration. So this thing is accelerating in this direction, so it's going to have a tangential acceleration. And also, it's got a speed, because of the speed, it's going to have a centripetal acceleration. So how do you know what the total acceleration of the system is? So at this point, it turns into vector calculus. Calc 3, if you haven't taken it, not a big deal. You can still learn it in physics. All right, so what you need to do is, you've got these vectors. So vectors got magnitudes as well as directions. The thing is, you're not changing the direction and the magnitude of a vector. You can just move it around. So I'm going to move this here, so I'll make a small triangle. So this is the centripetal acceleration, and this one is going to be the tangential acceleration. So you end up getting a hypotenuse. Hypotenuse is going to be the summation of these two vectors. So that's your total acceleration. Square of the base plus the square of the height is going to give you the total acceleration. All right, so it's got direction. The direction is going to be measured with respect to the radial direction which is directed towards the center of a circle. So opposite of the adjacent is going to give you the tangent of the angle, take the inverse of the tangent, and then we're done. All right, so if you have two different accelerations, you have to do a vector addition, and that's how it is done.